Lab for circuits and capacitors. So for this lab, we are predicting the behavior of circuits containing resistors in series and parallel using multimeters to measure the actual values of conventional current and potential differences in the circuits and examining the behavior of ohmic resistors and capacitors. So some key concepts that we used were the conservation of charge, which is a total charge of a system is constant, Kirchhoff's circuit laws, which for the loop rule, the sum of all potential differences around a closed loop is equal to 0, and the current rule, which is the sum of all currents in a system of conductors at a point is equal to 0. Ohm's law, V is equal to IR, circuit steady state, no charge in the overall voltage over a long period of time. So for this model, we modeled it online using the previous equations. The system was the circuit, the surroundings was the earth, and all other things in the digital model. Some assumptions were that the electromotive force, EMF, is equal to delta V cap plus delta V res. Part 1, we consider a simple series circuit of 2 batteries, 2 resistors, and 2 ammeters, as shown in the diagram above, and we predict the currents I1 and I2 that would be measured by the 2 ammeters. In part 2, we investigate RC circuits to observe how capacitors charge. So in here, for part 1, we found that the current was 0.02 amps. And we also calculated this using Ohm's law and Kirchhoff's laws. And when the connections are reversed for both ammeters, both ammeters read negative 0.02 amps, which is to be expected. When the voltmeter is put in place of an ammeter, voltage is equal to 3 volts and current is equal to 0 amps. Since it's an open circuit, no current can flow in the circuit. In the closed circuit, we measure the potential differences between A and B is 3 volts, B to C is 0 volts, C to D is negative 2.04 volts, D to E is 0 volts, E to F is negative 0.96 volts, F to G is 0 volts, and G to H is 0 volts. And so this means that when we add it all up, the total voltage is equal to 0. There's no charge in current. The voltmeter has a high resistance and doesn't carry any current. And here is the approximation of our potential differences as shown on this graph with the red lines between here. And because we split the node, and since the ammeter has a resistance of 0, which would decrease the resistance of the overall circuit, meaning the current increases, the ammeter readings increase to 0.6 amps. And here, using this equation, we were able to determine the values of R for each component, so for both the resistors and for the wires and the ammeters. So for part 2, we used these bulbs and one battery and a capacitor. So one bulb was 10 ohms and one was 20. So for the battery and capacitor with 10 ohm bulb, the light starts out bright but quickly diminishes in brightness and quickly goes out, and the current stops. This displaying charging behavior. With just the capacitor and the 10 ohm bulb, the same thing occurs where the light starts out bright but then quickly diminishes and then the current stops. This was discharging behavior. The same thing occurred in the 20 ohm bulb, just different times. So the time it took for charging and discharging was around 15 seconds for the 10 ohm bulb. And for the 20 ohm bulb, it was the same thing, except for charging and discharging was around 26 seconds. So this is how we took a graphical analysis, and our graphical analysis showed that our 1 over RC, negative 1 over RC should be about 6.8 seconds. So RC is equal to resistance times capacitance, and so we use that to also find it using the known values that we used in the model, and we found it to also be around 6 seconds. So our expected and our calculated were about the same. So for our what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? So the ammeter would have resistance and would contribute to a lower current than what was seen in this lab. For our other what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? how quickly would your ideal model predict the capacitor to reach full charge? So we would predict it to the capacitor would fully charge almost immediately because there's no resistor to slow down the current. In real life, however, this wouldn't happen since wires would normally have resistance, which would cause the capacitor to charge slower. Thank you.